Most people solve this problem wrong. They focus on energy loss instead of energy requirements. One tiny greedy trick changes everything.
Hi everyone and welcome back. Imagine you have a list of tasks. Each task costs some energy, but also requires a minimum amount of energy before you can even start it. Now, here is the challenge. What is the minimum initial energy needed to finish all tasks? And the tricky part, doing tasks in the wrong order can completely destroy your answer. In this video, I'll show you the greedy trick that solves this leetcode problem in just O of n log n time. So let's understand the problem. Each task has two values, actual and minimum. The actual means the actual energy consumed to complete a task, and the minimum is the minimum energy required to start a task. For example, if our task equals 4 and 8, that means that we lose 4 energy after finishing it. But you must have at least 8 energy before starting it. Our goal is to find the minimum initial amount of energy needed to finish all the tasks. The entire problem depends on the task order. So let me show you why. Suppose we have two tasks. For example, let's say we have a task where the actual is 1 and the minimum is 7, while we have another task where the actual is 5 and the minimum is 6. Let's name the first task A and the second task P. So if we do task B first, we lose a lot of energy early, which makes task A harder later. But if we do task A first, we can reduce the required starting energy. So the question becomes, how do we decide the best order to start our tasks? And the greedy idea is incredibly clever. For every task, we calculate the minimum minus the actual. Why? Because this tells us how demanding the task is compared to how much energy it actually consumed. So large difference means this task requires a lot of energy, a lot of starting energy. So we should do it earlier, while a small difference between the actual and the minimum tells us that we can postpone it safely. So to solve this problem, we have to sort the tasks based on the minimum minus the actual in ascending order. And after the sorting, we just simulate the process. We will, for example, maintain a variable, let's call it energy, and for every task, we need at least minimum energy before starting. But after finishing, we lose the actual energy. So the required energy became the maximum between the current energy plus actual and the minimum. This formula guarantees enough energy to start the task and enough energy to survive all previous tasks. So we sort tasks based on, first, we sort tasks based on the minimum minus the actual, and then we simulate the process. So let's go through the code step by step. First, we will sort our task. We give it the begin iterator and the end iterator. And also we define a customized function for the sorting. And here we sort the task based on the minimum minus the actual. And after that, we define our variable. Let's call it energy. And then we iterate over our tasks. For readability, we can define two variables. Let's name it actual, and this will have the first element of the vector and minimum, and this will be the second element of the vector. And finally, our energy variable will equal the maximum between the current the current energy plus the actual over the minimum. And finally, we return our energy. So again, first we sort the tasks based on minimum minus actual, and then this sort give will end up with the tasks with smaller gaps go first, and then we define our variable energy and initialize it to 0. This variable represents the minimum initial energy required so far. After that, we process every task in the sorted order. We define the actual and the minimum to hold the first element of the vector task and the second element of the vector task. So we just extract the task values for readability. And this here is the key line. It has two responsibilities. Either previous tasks already required enough energy, or this task's minimum requirement is larger. So we take the maximum. And finally, we return the energy, and that is our answer. In terms of time complexity, the time complexity here is n log n, and this is because of the sorting. And for the space complexity, it's O of 1, because we just used some variables. We don't define any extra space here. So let's run it to make sure it doesn't have any syntax error. Let's submit it. And here we go. This problem is a perfect example of a greedy ordering. The hardest part wasn't coding, it was discovering the correct sorting strategy. And that's it. If this explanation helped you understanding the intuition, please subscribe to the channel and so you can see all of our next videos, and see you in next video. Bye.